So I'm not going to do an introduction, and you can just, both of you can just take it away. I'm so glad that we were able to schedule this, and I look forward to your presentation.
Okay, that was a really rough start. Thank you, everybody, for being patient. Um, Leo's here too. All right,
He is.
great. All right, I'll just kick this off. Good morning, good evening to everybody, wherever you are. My name is Jeremy. Again, apologize for the rough start there, but got, I think we got it smoothed out and ready to go. Yeah, so I am a Postgres engineer at Geico. I'm going to be talking today about Postgres and Kubernetes. Um, Man, that really kind of threw me off, that whole start. I was kind of like in the zone. I had been looking at my slides this morning, and then I had to like troubleshoot Linux, Zoom, and headphones and audio stuff. So hopefully I'll kind of get back into my groove here. This is a little bit about my background and Leo's background, but we'll skip over this slide and kind of start in. Okay. Is my audio good enough that you can understand me? Because I'm using a microphone that I never use. I hope if I need to slow down or articulate better due to the quality, give me some feedback. Um, my good microphone is not working, so I had to kind of fall back to the laptop microphone, which is not very good. Um,
You're very audible, and we will tell you
okay.
if that changes. The only thing is your share thing. I'm not sure if I want to point this out because like it might mess with the presentation. But yeah, this window is sort of like over your slides. I don't know if you can change that at all.
It does. Look at that. I can.
Oh my
Excellent.
gosh, it's gone.
It
Perfect. Thank you.
worked. All right. Great. Wow, that was no, it worked. Okay. All right. So let's go. Three quick things before I get started. Last week I was so 2 weeks ago we were at KubeCon, and last week I rolled straight into the Pass Data Summit in Seattle. So it's been a busy 2 weeks. And there was a guy at the Postgres booth that made a comment. Ben actually said this. He said being a database administrator, he thinks is almost a little bit like being a specialized kind of systems administrator. And what he meant by that was if you're administrating databases, you really need to kind of understand the platform that you're running on top of. That's also true here. I really like Gabriele's blog here says exactly the same thing as he's talking about running Postgres on Kubernetes with this sort of pie-shaped profile idea. And that's what we're going to be doing today. Today, we're going to be we're going to be bringing together both distributed systems concepts and also relational database concepts. And you really have to be willing to kind of dig in a little bit into both of these areas. So I just kind of wanted to highlight that as a starting point. My second real quick introductory point is that, let's move my cursor over here. I just want to kind of highlight that the Cloud Native Postgres project has something called the CNPG Playground, which is a really, really great. I'm a hands-on learner. I learn things. I like to learn things by sort of playing around with the code. I'd encourage other people to try this out. It's really nice. In fact, I have a window up right over here with the playground. And then a side project of mine that I've been working on is just sort of creating this sort of a little thing on top of the playground where you can just spin up a virtual machine on your laptop or in the cloud and just get a quick one shot. It'll set up the playground for you and a bunch of other stuff. But I want to point that out. And last but not least, go click the big red button. The big red button takes you to the CNPG GitHub page. And I mention that because I think this is a very exciting time to get involved. It's an open source project, and there's a ton of areas where people can make contributions. I just threw 10 of them on this slide here that I think are places where people could contribute right now. Just these are things that are top of mind for me, but yeah, it's a really exciting time. There's a lot of opportunities to get involved. Today, we're going to be talking about just one of these areas, which is cluster management and failovers. So before we can really dive, agenda too, as we get started. So the thing, I think I'm looking at some of the names in here. I see a couple familiar names, but for those of you who aren't familiar, the thing that we're talking about today is this little thing that showed up just a couple of weeks ago in the release notes for the release candidate for version 128, if you didn't see this. And it has this little thing in the release notes that says quorum-based failover. What does that mean? That's what we're going to be talking about today is what does that mean? What is quorum-based failover? Why do we need it? What's the design? How does it work? The general format is that first I'm going to go talk about sort of some of the background and then what the high level design is. And then I'm going to hand it over to Leo. He's going to sort of dig into the details, talk about how it works, kind of how we built the engine, pop open the hood. So, okay, with that background, before I really get into the background of the quorum-based failover, I first need to kind of lay a little bit of groundwork, a little bit of foundational stuff. And this is going to be kind of your relational database primer. So first thing, does anybody recognize this guy on the slide? Type it in the Slack chat if you recognize it. Anybody? You got like 5 seconds before I tell you. I don't see it. This is, if you didn't recognize it, Jim Gray. So very well-known guy. I think could be considered one of the fathers of relational databases, and he was one of the first people to really articulate the idea of what a transaction is. It's something that we take for granted now, but it wasn't an idea that was always ubiquitous when you're talking about databases like it is today. This has also sort of been summarized with the acronym ACID, if you've heard that before. And this is a very, very relevant and important and timeless concept. Most importantly, because what this is it's a promise that we're able to make to our developers and our customers who work on top of our database platforms, which enables them to build applications faster, makes it easier to build applications. Because you don't have to worry about all these corner cases and edge cases in your application code. The ACID acronym, quick refresher, is atomicity, consistency, isolation, and durability. I'm not going to go super deep into all of these, but the one that I want to sort of look at a bit closer today is the last one, which is the durability area. And this is, in particular, this is about transactions, remember? And what durability talks about is that there can be failures in the system and the transactions are safe, like they're not going to just disappear. And this is a really important promise that we make to our customers, to our developers, right? Now, I want to kind of point out that you can delete all the rows you want. You can insert rows, you can modify rows. We actually don't make any promises whatsoever. You can do computations until you say the magic word commit. This is kind of an important kind of fundamental thing to understand. If you understand this concept, other things will make sense as you're kind of working with Postgres. We make no promises until in every language, every programming language. I have a few examples up here on the screen, but every programming language has this construct that you have this transaction, that you commit the transaction at the end, and that's the point where we make a promise to our developers that even if there's failures in the system, we're not going to lose that data. Now, Postgres itself is really great about this. You can go to postgres.org, download the database, run it on your laptop, pull the battery out, unplug it from the wall, kill the processes, and your transactions will be there. They won't be lost, right? If you're worried about like your laptop getting broken, you can even go download Postgres code from postgres.org and install it on another machine. And you can point that at the original one and it will replicate data to the second one, right? In Postgres terminology, this is called often called a hot standby or a replica. You'll hear those terms. And this will replicate the data between the two things. And Postgres also, for a very long time, has had pretty good it keeps the promise based on this replication. So what I've highlighted here is this is almost 20 years ago now that Bruce Momjian added this table to the Postgres documentation, right? And you'll notice right here in 2007, like the Postgres code and the Postgres developers were already thinking about that durability, that promise that we make to developers that even if the primary database fails, we're not going to lose data. The transactions will still be there. Now, you do notice in the table, it does have that little caveat, says with sync turned on. We'll circle back to that in a little bit. But the promise that we make to our developers, which is going to be based on replication, replicating the data, is that we won't lose those transactions. Now, I do want to point one more thing out, which is that also in the Postgres documentation, there's this kind of now, I was working with databases in 2007. I was more working with Oracle than Postgres at the time, but I do remember that in 2007 and in the mid 2000s, late 2000s, when I was working with databases, I wasn't usually working with like thousands of databases myself. I was often working with a smaller number of databases. And they were more like pets than they were like cattle. I kind of knew how they were set up. I knew how the replication was configured. And the thing about this, I like this sentence here. It says like synchronous replication can give you more durability if the sysadmin is cautious about the placement and management of the two servers. And there are two things about that sentence that jump out to me. Number one is that there's a sysadmin, and number two is that there are two servers. And this is kind of spot on, right? Like back in the mid 2000s when we were managing, it usually was like most often it was two servers, and there was always a human in the loop. There was always a DBA or a sysadmin kind of monitoring things. So this is still a valid deployment model today as well, is the other thing I kind of want to just sort of slip in here as before we kind of dive really deep into Kubernetes. That the way that I kind of think about it is if you're only managing a single digit number of databases, you don't need to be the team who goes to the VP and says, we should introduce Kubernetes at our company just for this. Like you can choose boring technology. It's something I like to say. There's a whole website dedicated to that. Just run Debian, install Patroni. You're good to go. And it's much, much simpler. That being said, that is a perfectly valid deployment model today. But it's important to understand, like for 20 years, Postgres has also been a lot more than just this. Because of Postgres's very liberal open source license, because of its extensibility, Postgres for many years has been sort of a platform. You could think of it as a platform. People have taken Postgres and done all kinds of things with it, right? They've built other products out of it. They've taken bits, they've built different things out of it. It's so something I've said, Postgres can run in your microwave. Postgres can run on a nuclear submarine. Postgres can run on hardware architectures and operating systems that you have never even heard of. It's very, very flexible. Postgres can even, of course, run on Kubernetes, right? But when you think about this kind of backdrop and what sort of Postgres, its versatility and its flexibility, including with the replication bits and pieces, this is the reason that Postgres itself, if you go download the database code from postgres.org, it has the core replication capabilities, okay? So Postgres can replicate the data, and it gives you the APIs that you need. But Postgres itself doesn't provide the bits and pieces to orchestrate. And part of the reason for that is because it's kind of intended to be very flexible. And there are people using Postgres replication in a lot of different ways. Like that sort of two-node failover cluster, that two-node failover cluster that like I was talking about earlier is a very, very common deployment model, but far from the only one. So Postgres will give you the APIs. Postgres gives you APIs to rewind a database, to configure and monitor replication. It'll give you the APIs to spin up a new database and restore it from a backup and do point-in-time recoveries, and then start replicating. Postgres will give you the APIs to take a replica and promote it into being a new writer. Postgres will give you all the APIs, but if we want to run Postgres on Kubernetes, one way or another, we're going to have to add some code that is able to do sort of the failover and the cluster management capabilities and to manage all of the Postgres replication. You're not going to get that from postgresql.org. Before I dive super deep into Kubernetes, I like to put these slides in. I did put another slide together, and I just wanted to point out that there are also loads of contribution opportunities at postgresql.org. If you're into relational databases, if this kind of stuff is interesting to you, one of the things I love about Postgres is how all the discussions are just right on the public mailing list. There's a whole bunch of really interesting ones happening right now, and specifically in this area of replication, there are a whole bunch of interesting places that you could still get involved. So if you're interested in database internals, I would encourage you to go check out the mailing list. And like there's some really interesting places and some open kind of like edge cases and challenging places where you could get into the discussions yourself as well. Okay, so now I'm kind of I wanted to set the background and talk a bit about Postgres itself, and then sort of the relational database pieces. And now I want to kind of start to shift gears and talk about Postgres on Kubernetes. The first thing that I need to point out, and I've kind of already pointed this out, is that Postgres's replication is extremely versatile. And the one of the unique things about the CloudNativePG operator is that it provides an unusually high level of access to Postgres's versatility with regard to replication. Now, why would we want access Why would we want a high-level access? Why would we want all this versatility? The reason is because there are different trade-offs that different people want to make when it comes to sort of those durability processes, those durability promises and guarantees that we make. Like it's actually pretty common to kind of like fine-tune the trade-offs and to tweak these. But before I can talk about how you actually make these trade-offs, the first thing that we need to do is just very quickly go through how do you actually configure replication, specifically with Cloud Native Postgres. I'm going to quickly glance at the chat. Okay.
That is
Thanks.
just me
okay, so
posting some links. All good.
Yep. All right, cool. Let's just checking if there are questions or anything. Okay. So the first thing is, before I get into the requirements, I just want to give you the tools that you actually use. So how do you configure replication in Cloud Native Postgres? There's basically 4 things that you need to know that I think are the big things. And then there's I mentioned 3 smaller ones in the bottom. I'm not going to get into those. There's a few other kind of minor things, but there are 4 big things you need to know, and I'm going to go through them one at a time. The first, and by far the most important thing, if any of you are running Cloud Native Postgres, this is the one most important thing you need to know, which is just how do you turn on synchronous replication. Now, you remember back to that original slide I showed from the Postgres documentation. The Postgres docs will tell you, like, you can guarantee not to lose data on a primary failure if sync is turned on. This is what it's referring to. It's referring to this synchronous replication. Now, I'm just going to really quickly show. On the left-hand side here, I have a little block of YAML. This is how you turn it on. This is really, really simple. I thought I would just show it real quickly on a CNPG playground. So on my screen here, this is the bare minimum. If you want to create a Cloud Native Postgres cluster, this is what you must have. Everything else is optional, but this is what's not optional. You have to have it. You have to tell it a name. The name is like, the name of your database. You have to tell it how many instances you want, and you have to tell it the size of your storage, right? If you remove any of these, it won't work. I tried, just to make sure. So this is your bare minimum. And if you want to turn on synchronous replication, which I had in the slide a moment ago, it is as simple as editing this file. And you can see I already have this cluster running. All you have to do is go edit this file, go to the spec. So you see I'm adding a section called PostgreSQL, adding a section that says synchronous. And I'm just going to copy, for starters, I'll copy what was on the slide. There's a method, and I'm going to put the word any. And then there is a number. I'm going to put the number 1. So just for starters, we'll just copy it, save the file, and quit out. Now, this is Kubernetes, so I will apply -f example, give it the file name. Oh, and I have a precondition that failed. Ha! Let me double check that I just didn't make a typo here. Method and number 1, and then I'm not going to troubleshoot this on the fly. You'll have to trust me. You'll have to trust me that this is the right thing for you to do, and I just have messed something up with my lab environment before I started this morning. Well, this is what you get. The demo gods are not smiling on me today. Last applied configuration, precondition failed. Oh, it's up at the top. Okay, we're going to skip this because I don't want to go too much over time. That's where you're going to add the block. I'm not going to troubleshoot this. If I have time at the end, I'll come back to it. I believe I did that right. PostgreSQL synchronous method any number 1. That's where you're going to put it in. So I just kind of cut and pasted from the slide. But the next question that you're going to ask is, what is this method and this number? What does that mean, right? So in order to understand what those are, what we're going to have to do is go back to PostgreSQL itself. And this is in the Postgres documentation, but what I thought would be a nice place to look was this commit message from 2016, almost 10 years ago. A lot of people don't realize it, but it's been almost 10 years that Postgres has had 2 different kinds of replication built into the core database. One of them is called priority-based replication. The other one is called quorum-based replication. And there's sort of one golden parameter that you really need to know about, which is 90% of what you need to know for replication in Postgres, and that is called synchronous standby names. I've circled it up at the top of the screen here. The synchronous standby names, it's a Postgres configuration setting. Sometimes they're also called GUCs. I think that stands for the Grand Unified Configuration, if I remember right. But it's a configuration for Postgres. This is the configuration that turns on synchronous replication, and the format, like the value that you put in here, has three parts. I've circled it at the bottom. It has a method, it has a number, and it has a target list. Those are your three things, okay? So the way Postgres itself would be configured to do synchronous replication is a method, a number, and a target list. And now, like when you look at this, the method is simply telling you priority or quorum-based, and the target list is a set of replicas where I might be replicating to, and the number is simply telling me how many replicas do I have to replicate to. So it's actually just that simple, right? So if I come back to here, the method in this example here, I'm just saying, so in my example that I had, which did not apply, I had 3 instances total. One of those will be a writer, 2 of them will be replicas. Remember, Postgres is a single writer database. And here, what I'm saying here is I'm saying that it has to be replicated. The promise I make to my customer is that the transactions will be replicated to at least one replica. And it could be any replica. It doesn't have to be the first one. So that's what the method and the number mean. So that's the first piece. Now, the second thing you need to know kind of comes right on the heels of that, which is that Postgres is very literal. If you tell Postgres, I want you to replicate, I want you to always, I'm going to promise my customers the transactions are always replicated to one replica. Well, Postgres would take you very literally. And what happens if there is no healthy replica? For various reasons, because a node is unhealthy, because a node is being rebooted, a hardware failure. Well, what Postgres will do is if you have told Postgres, always send it to one replica, Postgres will just stop accepting any transactions, right? So like the moment somebody tries to run a commit statement, that commit statement is just going to hang indefinitely. It will never come back, right? Because Postgres is going to do exactly what you asked it to do, which was make sure the transactions are replicated to at least one replica. Now, sometimes this is what you want. You might want to provide a strong guarantee that every transaction is on at least one replica, but that's not always the case. Another thing that sometimes people want is that they might want that if I know a replica is unhealthy, don't take down the database. Let the database run while I fix the situation. And then once the replica is healthy again, I want you to go back to keeping your promises. Okay. So that is another way that you might want to configure things. In Cloud Native Postgres, the word that we use for this is called data durability. So by default, the data durability is required. That means that if I send it to one replica, it must be sent to one replica. However, you have the option to say my data durability is preferred. What that means is as long as there are healthy replicas, we're going to do that. But now this is not happening in Postgres. This is happening in the operator in CMPG. You're giving the operator permission to say, if a replica is unhealthy, the operator can temporarily relax that constraint. And it will reconfigure Postgres and reduce the number in the background so that Postgres stays online. And then once those replicas become healthy again, the operator will bring that number back up to where you want it to be. And once again, you're keeping your promise to your customers that the data will be replicated, that if there's a failure in the system, it's durable, and we will not lose any transactions. So that's number 2. Number 3 and number 4, I'm going to go really quickly. Number 3 is that you have very fine-grained direct control over the target list. And I'll show a little bit later a couple reasons why you might want that. You can prefix, you can suffix. By default, the target list just has all the replicas in the local Kubernetes cluster, but you can also control that. And the fourth thing is a Postgres setting called synchronous commit. And what this does is it enables you to fine-tune the replication behavior. When I promise to my developer that the transaction is replicated, do I just mean it's been received by the replica? Do I mean it's written to the disk in the transaction log? Or do I mean that it's actually been applied to the tables and the indexes on the replica? This is the setting that controls that. The default behavior is that it should be written down to the transaction log or the write-ahead log, but you can change that behavior with this Postgres setting. Okay, so once you have those 4 tools in your tool belt, now we can circle back to the different trade-offs I was talking about. And I really like the Oracle terminology. So what I've done here is I've kind of borrowed Oracle's terminology from the Oracle Data Guard configuration, and I've kind of mapped it across to show you how you would do this with Cloud Native Postgres. So within a single Kubernetes cluster, here I have an example with a primary and 2 replicas on the screen. And you can maximize your performance, which is kind of the default configuration, meaning everything is asynchronous. There could be some data loss if there are failovers. You can also maximize your availability of the data. This is maximizing availability of data. That means that as long as replicas are healthy, we're going to guarantee it's been replicated. But if the replicas are unhealthy, we'll keep the database up. That's maximizing availability. And this is where you see the data durability option coming in. And the last option you have is to maximize your protection. If you're maximizing your protection, you're saying, I'm always making sure that the data has been replicated. And that's without the data durability. That's sort of the default. That's, in my opinion, that should be sort of a minimum for you. The availability is also something worth considering. But this is just the beginning. There's actually a whole bunch of other stuff we can do too. So this is within a single Kubernetes cluster, but what if I want to have multiple Kubernetes clusters? And this is really common for something like disaster recovery. So you could have a Kubernetes cluster on the East Coast, another on the West Coast, or maybe you have one in the EU, one in the US, kind of whatever configuration you want. But you can have multiple Kubernetes clusters. Now, something to note is that the Cloud Native Postgres operator only directly manages within a single Kubernetes cluster. So you're not going to get like automatic failover and things like that. However, you can do all of the replication, and you can make all of the same trade-offs that we were just talking about within a cluster. So by default, you get a maximum performance type of configuration where everything is asynchronous. And if like you yourself were to try to do a promotion or a failover, and you didn't manage it carefully, there could be the possibility of some data loss, right? If you lose the primary and the data hasn't been replicated, or you can maximize your availability. And now we start seeing where we're controlling that target list that I talked about earlier by prefixing it with the remote cluster. This is also the one example where we use priority replication. Priority replication is what enables us to have a configuration where if the remote cluster is unhealthy, the database stays online and continues to accept writes locally. Or you can maximize your protection. And here's an example of that. And here's an example. And if you didn't catch this, on the left-hand side, I'm showing the YAML that you would put into Kubernetes. And on the bottom, I'm showing you how that comes out in the database configuration, okay? So the synchronous standby names, that golden parameter, that is the most important Postgres configuration for replication. But this isn't all we can do. There's still more. The thing about maximum protection mode is that I'm guaranteeing there's always my transactions are going offsite to another Kubernetes cluster, maybe in another data center. But the problem with this is that like if there's network disruptions or if there's problems over there, I stop accepting writes, and a lot of people don't like that. One of the ways to deal with that is maximum availability, but another way to deal with it is to have multiple offsite locations, just like we're doing in our local, and you can do that too. So here's one example configuration. There's sort of 2 ways you can do this. I'm just showing one of them here because this will make a good example later on for something else. But here's an example where we have 2 remote clusters, and we're always guaranteeing that my transactions go to at least one of the remote sites. But one of the remote sites could be unhealthy, there could be network problems, and my database would stay up. As long as one of the 2 sites is online, I'll continue to accept writes. So that gives you a sense of just how much you can do with Cloud Native Postgres, but this introduces a problem. The problem is, with all of these different configurations, how in the world are we supposed to write failover logic and like keep it manageable, right? And I've looked through some of the failover logic from for a lot of different products. Kind of, I've just had opportunities over the years, and this stuff does get really complex very quickly, especially when you're dealing with a lot of different possible configurations like we have here. And this is a challenge that like I was thinking about, and I know other people were thinking about over the past year or two, is just how do we manage this, and how do we make sure that we can not only keep it maintainable, but also know that there's correctness. that we don't ever make an incorrect decision as far as when to do a failover or when to promote a replica or any kind of a cluster reconfiguration, really. This seems like a really, really hard problem, but as we were thinking about it over the past year, the realization came to us that there was a very simple and elegant solution to this that really just takes an old idea that's been around for decades. The idea is that we sort of look at the basic idea behind Quorum. And what we're going to do here, I'm going to sort of jump to this. So this is a photo that Leo took of his whiteboard, because when you're trying to do open source software and you have like people all over the world trying to collaborate, like this is what you do. You like take pictures of whiteboards and like post them on Slack. So I cleaned this up a little bit. And what we've got here is the sort of basic quorum formula, which is that readers and writers have to be greater than your replication factor or your node count. And this is something that's been talked about a lot. It's not new. It's been around for decades. But what we realized is that we could take this basic formula, this basic idea, and we could map these sort of ideas over to Postgres and use this for solving the problem of how we handle all of these cluster reconfigurations, all these different situations. And here's what we've done. The n value, which would be like your node count or replication factor, is basically the target list from that parameter, that synchronous standby names, the all-important parameter. The w value in this formula becomes the number from that synchronous standby names parameter, okay? And then the r value is something, oh, and I should sort of say, so what we're doing with this formula is we're basically going to turn this into sort of like a gating function. So whenever we want to do a cluster reconfiguration, any kind of like just reconfiguring, changing how replication is configured in the cluster, first we're just going to use this as a pass-fail check to say, is it safe to sort of proceed with a cluster reconfiguration? And the R value, we're only going to evaluate that when we have to sort of like make one of those decisions. And the R value, what that is, it's the intersection between the set of targets for replication and the set of promotable replicas. So it's the intersection of those two things. So kind of a couple other kind of minor notes, which is that we can block any cluster changes by zeroing out the W value. And then we kind of like, for managing state changes, like you do have to think really carefully through state changes in the code in the order that you change variables. So like, because you can have intermediate states and you have race conditions, right? So like really simple rules for state changes is that your R and W values can always be too low, but you don't want them too high. Your N value can be too high, but not too low. The basic idea here is that like you want to err on the side of not allowing cluster changes, rather than erring on the side of accidentally allowing a cluster change to happen in some tiny window of time when it shouldn't have. So following these rules kind of just sets you up for that. So the best way to explain this, I think, is just to look at some examples. So let's start with our example where we had a replica cluster and we were doing maximum availability. So this is the one where we want synchronous writes to that second cluster as long as it's healthy. But if it's unhealthy, we'll stop doing synchronous writes. So we're using priority replication. I've got the configuration here. What is our N value in this example? So remember, the N value is coming straight from synchronous standby names. So you look at the bottom slide, and the same with the W value is also coming straight from that. So the N value is 3. I've circled them. It's those three, the 2 local replicas and the 1 remote replica are synchronous replication targets. And our W value is 2. You just take it straight from the setting. What happens if the primary node fails? Okay, the primary node fails. Now we have to make a decision about whether we can promote a replica to be a new primary. So this is when you sort of see the set of promotable replicas are the 2 local replicas. Now it does not include the replica in the remote cluster. That's not promotable, right? Because the operator can't promote that. It only works within a single Kubernetes cluster. So our R value is 2. It includes both of these. Our N value is 3. 2 plus 2 is 4. That is more than 3. That means we have a green light, thumbs up. We can go ahead. We'll choose whichever replica has the most advanced LSN. We can promote it, and we're good to go. Now, what about the maximum protection example? This is the one where if the remote cluster is unavailable, we stop accepting writes. Okay? So you have at the bottom here, the N value in this example is now going to drop down to 2. right? If you look carefully, and the W value is also 2, and this is by design. What happens if the primary fails? Now you can see where that intersection comes into play, all right? In this example, the primary has failed, and both of our local replicas are promotable from the perspective of the operator, but you have to do that intersection. So our R value is 1, not 2, because it's the intersection between the set of the set of targets and the set of promotable replicas. Nonetheless, 1 plus 2 is 3. 3 is more than 2. The check still passes. We have a thumbs up, and we can continue to promote. We're going to wind up promoting replica ACDC2 in this example. Next example, something a little bit more fun and interesting. What about the case where we have 2 remote replicas? Well, in this example, our N value is going to be 4 because we have both of the remote replicas and both of the local replicas. Our W value is 3. We always have to have writes to 3 of those 4 replicas. And if the primary fails, our promotable replica set is only the local replica, so it's 2. 2 plus 3 is 5. 5 is more than 4. Check mark, green light, go ahead, and we'll choose the most advanced replica. But what if one of those replicas happened to be sitting on the same server as the primary? And so that means that we lost both the primary and a local replica at the same time because the server failed, the power was pulled. Well, in this case, we only have one promotable replica because we lost one of those replicas, right? So now our R value has dropped down to 1. And in this case, now the check fails and the cluster has to go into a state where some kind of manual intervention is required by an administrator. Now, this is an interesting situation because if you think about it, in all likelihood, that local replica does have all the transactions because usually your remote clusters are on slower network connections. Usually one of those remote replicas is probably the lagging replica that doesn't have all the transactions. One of them is going to be a little bit behind, like maybe not by much, but a little bit. But we can't guarantee it, right? And that's the thing. There can totally be situations where for one reason or another, network issues. I mean, we're having failures. Like when you're having failures, there can be all kinds of things. You never really know the state of things. It could very easily be the case that both local replicas, there were network issues going on locally, and you can't guarantee that local replica has all the transactions. So this is the correct decision, even if it seems like, well, but it probably would have the transactions. The correct decision, if you want correctness, is that don't automatically promote that replica, but wait for manual intervention, wait for an administrator to come actually make a decision about what you want to do. All right, lastly, let's look at a couple, just to sort of wrap things up, look at a couple network partition cases. And when we start talking about network partitions, we have one new variable that we have to add to the equation, which is what is the location of the operator itself? Because the operator is the thing that's evaluating the health and making the decisions. So in this, just sort of starting out with an easy one, we have the case where the primary gets dropped off on a network partition, but the operator and both replicas are on the other side of the network partition. In this example, our N value is 2, our W value is 1. The operator can see both replicas. So from the operator's perspective, there are 2 promotable replicas. 1 plus 2 is 3, 3 is more than 2. We'll go ahead and we can promote a new primary from one of those replicas. Now, important question. Why is this not a split brain? That is actually a very important question and maybe not obvious at first. There's sort of 2 answers to this. This is the most important answer is synchronous replication. Remember, you have synchronous replication configured this example. The moment the network partition happens, that primary instance immediately stops accepting any transactions. And this is one of those things that you have to realize that maybe it sounds like a bad thing for that primary database to stop accepting transactions, but it's actually protecting us. That's the behavior we want to protect us from losing transactions in situations like this. You need that primary database to keep its promise about data being replicated. And that's what really ultimately protects you from a split brain in a situation like this. Now, something I've kind of become aware of over time is that historically in the Postgres community, there's been kind of a willingness to kind of make other trade-offs. And one trade-off in particular is to not use sync replication in situations like this. So you can have something like a fail-safe that will just sort of like monitor in the background and just try to like kill the primary. This is possible with CNPG. This is also possible with other technologies. But I want to point out, and I think this is important to understand, that even in that approach, there's always a window of time where you're going to lose a few transactions. And so it's just an important caveat to be aware of if somebody wants to do that kind of a configuration where you're not relying on the synchronous replication, and you just want to have like some sort of a fail-safe logic that's in there that tries to kill a primary. And this, like I said, there are multiple softwares out there that do this. CNPG will allow you to do it. I'm a proponent more of just like always turning on synchronous replication, as I've said a few times here, because that gives you the strongest guarantees. It gives you guarantees. There are no guarantees outside of it. That's the only way to really have the guarantee that you don't lose transactions and keep, in my view, keep the promises that we need to keep to our developers. All right, next one. This is a little bit boring, but if I partition off one of the replicas, really not much happens here. But this is the example where you notice, because one replica has remained, the primary database continues to accept transactions and it is uninterrupted. We don't have to wait for a cluster reconfiguration. We don't have to wait for the operator to notice that the replica is down and reconfigure synchronous replication like you would need with data durability. This is the advantage of using quorum commits where you only need to go to one replica while there are two replicas available. No interruptions at all. Database just stays online the entire time. Potentially the unreachable replica could be replaced, but there's no promotion or failover needed. All right, finally, let's look at a really interesting one, which is this one. And this is the case where I have a network partition that puts the operator in one replica on one side of the partition, and I put the primary on the other side of the partition with a replica. This is a really interesting situation. So first of all, let's run the numbers. Our n value is 2. Okay, our w value is 1. You can see that from there, the red lines. Now the set of promotable replicas, or R value, is from the perspective of the operator. And in this example, the operator only sees one replica. Okay, so from the operator's perspective, the R value is 1. 1 plus 1 is 2. The check fails, and the operator is blocked from doing any kind of cluster reconfigurations. The operator will not promote that replica to be a new writer. Is that the right decision? In this example, it is, and this is important to understand because remember, in this example, off on the other side of your network partition, the primary has a replica, which means that that primary, it's continuing to accept transactions. Like when that network partition, and again, like even if you have a process like a fail-safe process that will go in there and kill the primary, you cannot avoid that small window of time. There's always going to be a window, at least a small window of time where a couple of transactions are going to go in. They're going to be acknowledged to the client. The client is going to assume that those transactions are durable and committed and saved, and that they won't just disappear. And if you were to do any kind of an automatic promotion, and if you were to promote the replica, you would lose. So this would legitimately be a split brain, at least for a few moments. Even with the failsafe, if we were to make a promotion decision. So technically, if you're going for correctness, if that's what you want, the correct decision to do in this situation is to not promote, to not make an automatic promotion, not self-heal, but to wait for manual intervention. Wait for an administrator just to make a decision about like, am I okay with accepting the potential loss of a few transactions to bring the system back up? Or do I need to just wait for the situation to resolve, maybe resolve it in a different way so that I know and I have the guarantee that I haven't lost any transactions at all. So that goes through, I think that kind of walks through the high-level algorithm, why the design is the way it is. And again, this is like setting the high bar on correctness and trying to make sure that we keep our promises to developers 100%, that we don't and can't lose any transactions. At this point, I think I'm going to hand it over to Leo to dive in a little bit.
Thank you. So first of all, I need to say thank you to Jeremy because I'm part of the original team that designed this operator, and seeing CloudNativePG explained by someone outside the team, and in this way, it is really, really satisfying to me. It means we did something that, I mean, it resonates with other people too. To me, it is wonderful. So yeah. Beside this, how does this work? Okay, as Jeremy mentioned, this is implemented starting in version 128. And to enable it, you need to use the failover quorum field inside the synchronous replication configuration stanza. So just again, we need to, this is inside the synchronous replication configuration. This is meaningful. It means that synchronous replication is really important for us. It's there for a reason. When we do this, the operator will start creating a new resource, which is called failover quorum. Can you go to the next slide, Jeremy, please? Okay, that's it. That's it. So the operator will create a failover quorum resource, just like the one on the left, without the status section, just empty. And why we do this? We do this because the failover quorum resource will contain all the information inside the synchronous standby names configuration settings. But the operator doesn't really know the status of Postgres. The only one that knows this information is the instance manager. This is the PID one, the really small process that is inside every Postgres pod. So yes, the operator will create this resource but empty, and then the instance manager will update it. More precisely, only the instance manager of the primary node. And as you can see in the status section, is more or less parallel to the synchronous standby names value. If you can method any, synchronous standby name starts with any, then you have one, which is the standby number, and inside parentheses you have the standby names. There is only one field which is called primary. This is just the name of the pod that updated the failover quorum resource. Okay, this is easy. So good, next slide. So why we do all of this? We do all of this to evaluate our magic equation that Jeremy explained. But to do it, we really need the latest possible data. We need to be sure of the data we put inside the equation. And we are lucky because with CloudNativePG, the configuration is totally managed by the instance manager, in the end by the custom resource called cluster. So it's there. There is no user intervention that can manually change the configuration unless you do it and you enable it. In that case, you are responsible for what you do. Okay. But yeah, still, suppose you change a parameter inside your cluster section. How can be sure that really Postgres received the configuration change? So next slide. So we need to go a little deep on how we apply a new Postgres configuration. So we generate the new configuration. This is fun. Good. We update the configuration files. Okay, it's great. Then we reset the failover quorum custom resource, and this is weird. Why do we do that? Because we are going to change the configuration of the system, and until the new configuration be received, we are not sure if the old configuration is in place or the new one. So we reset the failover quorum resource. In that case, 0 plus 0 is not greater than 0, and there will be no automatic failover, okay? Again, we are setting the high bar as Jeremy was saying. Then we sig up the postmaster, and this is asynchronous. The postmaster will eventually receive our signal. This is usually really quick, but it's better to be correct. Then we wait until the postmaster receives the configuration, and then with this configuration we update the failover quorum resource. But we need to go a little deeper. So next slide. What do we do? Every time we create a Postgres configuration, if the failover quorum feature is enabled, we set a new parameter that is called synchronous standby names metadata. As you can see in this slide, this is just a JSON representation of what is in the synchronous standby names parameter, easily parsable by the instance manager. And then we seal the configuration, we stamp it with a hash, just to tell, look, this configuration has this hash number, okay? And you can find this hash number in the cmpg.config sha parameter. Good. Next slide. Now we keep querying Postgres until we receive the hash that we are waiting for. So when Postgres go back to us telling, look, this is my hash number, in that case, we are sure that Postgres loaded this configuration. So this is how we can be sure that really Postgres received the change. So next, when this happens, we use our magic JSON data inside synchronous standby names metadata to update the failover quorum object. Now the operator is able to trigger an automatic failover if the magic equation criteria are met. So next slide. And now we have the problematic point when something terrible happens because your primary is not ready anymore. We need to evaluate all the data we have, and we use what you have seen in the status section of the failover quorum object to evaluate the equation, nothing more than that. And if the criteria are met, we proceed with an automatic failover. Otherwise, the automatic failover is prevented. That means your system wouldn't accept any new transaction. This is the price to pay for correctness. You can't have everything in this kind of systems. Good. Next slide. Okay, so these are two examples from Jeremy's slides. I just added the log messages you will find in the operator logs, and I think these are useful to understand what's happening under the hood. So this is the really easy example when you have a cluster with 3 instances. The instance number 1, you can see this in the bottom left, is the primary. You requested one synchronous replica, and the primary got disconnected or something happened with it. So you will find something like what's on the right in your logs. You will find that the system evaluated that this is a situation with strong consistency. This is exactly what Jeremy shared. And you have explicitly the read set, so the R as a set instead of as the cardinality, and the node set. You don't have the write set as a set. This is exactly where this equation is really great. It speaks of cardinality and doesn't require knowing the exact names inside it. So in this example, example 2 would be promoted because we suppose example 2 to be the most advanced replica. So next slide. This is more interesting. So it's just the same as before, but here I disconnected example 2 and example 1. So we requested to have one instance, one replica, one synchronous replica, okay? Before the damage here, we have everything up and running. So the primary was accepting transaction, but we requested just one replica, and we don't know if that replica was example 2 or example 3. So when example 2 got disconnected with the primary, we don't know if we are correct to promote, if we need to promote example 3 or not. Example 3 could be the replica which is synchronous. In that case, I mean, it would work. But otherwise, if example 3 was not the synchronous replica, you would have lost data here. So this situation is not strongly consistent. So that means there is a possibility that you may lose data. In this case, as you can see, you have the read set that compared to the previous slide is only composed by example 3. And that comes out as 1 plus 1 is not greater than 2. So this is blocked. And you will find this message in your logs, strong consistency check failed, preventing failover. So you would have no primary and you need to have manual intervention here. Okay, I guess I'm done. Next slide, but that's it. So if you have any question, I don't know if we have enough time, Flor. No, it's like we are a bit late.
I think we are over the time for 4 minutes. So we are good if someone wants to stay longer, but I don't think it is. Anyway, we are going to keep the recording and we are going to upload it to the CloudNativePG channel on YouTube. Okay. And with that being said, please, any questions, you can unmute yourself, obviously, because this is an open call. Turn on your camera if you want. Remember that this is recorded and go ahead and ask. Please ask.
Wow, I scared everyone.
It's not an easy topic. As we can say that it's not easy, and we know that.
No.
We always knew.
I don't have a hard question. I think I have an easy question. I think I know the answer, but I just want to confirm if the behavior would be right. So in case of a network partition where the operator is isolated with one of the replica, right, which is not a strong, consistent state, and there is nothing to promote, so we're going to be stuck in that case. And the network partition recovers, right, and the primary comes back up, right? What does the operator do? Does it just leave the existing configuration as is, or does it try to re-evaluate the primary secondary quorum? What happens at the time?
It would just leave the same replication configuration as it has before. If you like to, and if you are willing to do it manually, you can still promote the remaining replica. But before doing that, you need to assess your situation to understand if you are really going to lose something and you can afford losing it.
Gotcha. Okay. Yeah, that makes sense. I think that will be a expected behavior. Cool. Thank you.
Yeah, we usually
I have
prefer to do nothing if there is any risk.
Makes sense. Yeah.
a question, or follow up to that. So in this example here, because I'm actually not sure, I haven't tried this to see what happens yet, but so like in this example here, that's on the screen, the network partition, like nothing will happen. So the quorum will block the promotion. Now, let's suppose that like 2 hours go by and then the network situation is resolved on its own, right? So now the operator is able to, well, I have to think about this. Actually, there's the failsafe feature will probably kick in. If that's enabled, that will kick in and kill the primary. So the primary the instance manager on the primary would probably, I don't think it would shut down the pod though, would it? The pod would probably keep running, but it just wouldn't start up.
But the problem is that here we are talking about the operator, but really the most important point here is the API server. So even if the operator is on another partition separated from the primary, but the primary still reaches the API server, it will not shut down itself.
I see.
But
Okay.
wouldn't the operator always be on the same side of the partition as the API server?
No.
Can it be different?
If it is this different, it won't be able to trigger any failover because there is no central
You're talking
data
about
authority to trigger.
the Kubernetes API server, right?
Mm-hmm.
Because so I think what's underneath all of this is etcd. So
Exactly.
etcd itself has to so if you have a network partition, etcd can't be on both sides of the partition, right? So etcd will have a quorum on one or the other side. And I think that whichever side etcd ends up, like I would, because the operator is going to use the etcd leases. Like I think it's going to land where, if there's no etcd, I don't think you have either an API server or an operator, right?
No.
Right. That's why I'm thinking that they would end up on the same side of the partition as etcd, wherever it lands.
The primary could still be taking writes.
The primary, yes, the Postgres primary could. But
Yeah.
to Leo's point about the API server and the operator, I'm thinking that both of them will follow etcd. But again, like I haven't done a lot of like failure testing around this and like chaos testing. But I'm thinking they should land on the same side of a network partition because they should both follow etcd, I think.
So actually, the source of truth for this situation is etcd and the Kubernetes API server. The operator is only a decider. If it gets disconnected from the API server, you won't have any failover by design. It's just one operator. And if cannot reach the API server or etcd, it won't be able to do anything at all.
Mm.
Yeah.
So
Will Kubernetes, but if that happens, if the operator is on the opposite side of the partition, will Kubernetes start a new operator?
Yes. Yes, after a
It
while.
would, right?
The operator is actually is a pod like all the other ones.
Right.
When that
So
node
yeah.
get disconnected, that pod will be evicted and then
Yep.
rescheduled in another pod, in another node. Sorry.
Yeah, I think if the operator gets partitioned off, it can't, without etcd, I don't think it can do anything. So I think the operator that is
absolutely.
partitioned off, will kind of be irrelevant. A new operator should get spun up on the same side as the API server. So I think you should still, there is an interesting, but see, that goes back to where like if you don't want to rely on the failsafe because you have all these like delays that can happen, right? Like the old operator, it could take a few moments for the operator to get shut down. And during that, yeah.
You have the leader election of the operator too.
Okay.
So yes, actually, when the pod will be evicted, the old pod will be evicted, a new one will come, and the new one will need to wait for the leader lock of the previous operator to expire before starting.
Yes, the lease. It's Kubernetes, or I mean, it's etcd leases, right? Yeah. So because I think we're just using controller runtime, if I remember right.
Yeah.
Right. So it's not like the CNPG, like there's no like leader election code inside of the CNPG source code. It's just you just use the operator runtime libraries and then you get everything for free.
Yeah. It's just the same Kubernetes use.
Yep. Yeah.
No, this is
that question. I've heard that question come up too. People wonder like if CNPG is doing its own leader election, or how does it work?
No.
And I think it's a lot simpler than most people think.
Yeah, it would be so error prone to implement, bro.
It's tricky.
Yeah, it's better to use something that is really widely used, if we can.
Cool. Thank you, folks.
Thank you.
Any other question? Please unmute yourself if you want. In the meantime, the usual information that you have the calendar for our meetings, community meetings, office hours, and everything is on the shop. You can join You can have your profile modified in openprofile.dev, as I started in the meeting. So if you have any questions there. Also, I can see that there's another meeting, and we are way over the time. So thank you everyone for joining. And a participant has enabled translation. Okay. Who was it? Anyway, thank you for joining. Thank you, Jeremy, Leonardo, for your time. This is amazing to have you here. It was great, great talk. Way longer than the one from KubeCon, I can tell. And was really beautiful. Love, Jeremy, your slides are wonderful, I have to say. No questions about it. Thank you. Your work was amazing here. And thank you everyone for joining. So we will see you in next talk, probably in a couple of weeks, months, I don't know. We should do this more often. It's kind of fun, okay? Thank you everyone. See you in the next. Thank you for everything. Ciao, ciao.
Thank you.
Ciao.
So